So the Test of Time Award was established now 13 years ago. The idea is to recognize papers that have had a significant impact in the storage community. The papers have to be at least 10 years old. The idea is that it's not just something that was cool at the time, not just something that earned a Best Paper Award, but something that actually has had influence, and so we want to give it time to have that influence. The selection is done by the FAST Steering Committee and past program chairs, with the process being managed by Raju and myself. I'm just going to flash up here past awardees. I'm not going to go over these. Just some of you can look back and see things that, oh yeah, I remember that paper, and that was a really cool paper, or my advisor made me read all of those papers, or something like that, in which case you have a good advisor. The process, this year we had 4 nominees for the award. We had 17 reviewers who submitted a total of 63 reviews. And then Raju and I reviewed the reviews, and we met in January to make a final selection, and we chose a paper that I think you will agree is a truly outstanding paper. The committee had some comments on this paper. One of them, I've seen commercial systems, both storage systems and database systems, that have taken inspiration from this work to provide customers and field service engineers insight into the expected effect of allocating more or less memory for their caches. Another reviewer said, this paper has really revolutionized MRC usage in online settings. As far as I know, it has the best performance of known miss ratio curve algorithms, or is certainly hard to beat and is very accurate. Another said, this paper made MRCs practical and popularized their use. In fact, we often use the proposed algorithm or variants in our company, and the folks that study cache policies view this paper as a landmark. Given those comments, some of you may have already guessed what the award winner is. So it is Efficient MRC Construction with Shards by Carl Waldspurger, Nohhyun Park, Alexander Garthwaite, and Irfan Ahmad. And we are lucky because they are all here today to be able to accept the award. And so at this point, I am going to turn it over to them. So please come on up. Take a moment to congratulate all of you.
So thanks, Jeff, and thanks to the award committee. We're honored to receive this award. Sure. And I'd like to just take a moment to reflect on the origin and context of this work. At the time, all 4 of us were working at Cloud Physics, which is a small startup focused on resource management and virtualized systems. And this research stemmed from a real customer challenge, a real-world problem. And that was sizing flash caches, which were becoming increasingly popular alongside traditional storage at the time. And it's a reminder that despite the relentless pace of a startup, good research can still emerge, and also that necessity often motivates the best ideas. We began by collecting I/O traces from customer sites and testing cache sizing heuristics, but the results weren't as promising as we had hoped. A more principled approach that we were aware of was to generate miss ratio curves, or MRCs for short, and that's a concept dating all the way back to Matson in 1970. However, even the best existing methods were too resource intensive, especially for large traces. And having used sampling approaches and techniques in prior projects, we explored whether sampling could make MRC construction more efficient. But it was challenging because sampling a large sparse address space while also tracking reuse is something that hadn't been done before. So the key insight was that using deterministic spatial hashing could be used to drive randomized sampling, and that formed the basis of the SHARDS algorithm. Some of our colleagues were initially pretty skeptical, but early experiments exceeded expectations. And at one point, the results seemed almost too good to be true. I even worried that perhaps we had a bug that was artificially inflating our accuracy. But it all worked out, and then we continued to develop a constant space variant of SHARDS that enables accurate MRCs to be built for any trace length in less than 1 megabyte of memory. And that makes it feasible for even the most constrained, resource-constrained systems. And between our original submission to FAST and our final camera-ready copy, we added preliminary results from applying spatial hashing to non-stack replacement algorithms like ARC or LERS, paving the way to our follow-on research in miniature simulation. So it's been really exciting to see people and others build on these ideas over the years, and we're deeply grateful for this recognition. Thank you.
Could we switch to the slides? Thank you. So I'm Irfan Ahmad. Thank you, Carl, our leader and first author for this paper and for much of the follow-on work. As Carl said, this was a very interesting time where we were looking back at the work in the area of memory resource management going back to the dawn of computing. And so whereas Carl's walked you through what led to this particular research, I wanted to start actually pretty far back. I mean, let's go back to the beginning and share some things that we learned that many of you may know, but some may not. So as we were looking back and trying to, again, understand memory resource management and placement algorithms and what oftentimes we just call it caches, we went back and looked for, where did it all start? So this picture here is the console for the Atlas system, and the paper that describes the virtual memory for this is 1962, which means this paper, the work is probably about 1961 as far as I can tell, because I tried to look around and to figure out when was this work done. As far as I can tell, the system was shipping when this paper was published in April 1962. So actually, it's a remarkably good paper. When I read it, it felt like I was reading a paper published 2 days ago in 2016, 17 when I found this paper. It's written really, really well. And all we have to do is kind of replace the word drum with SSD and the word core with DRAM, and it would make sense, actually. It could probably get into fast, now, today. Well, don't get any funny ideas about trying that, though. Okay? So this machine had use bits and therefore was trying to manage memory, using that. But it's the first virtual memory system that I know of. We were talking earlier, none of us could remember anything earlier than that. But interesting thing, why this was relevant was because this machine, as innovative as it was suffering in the field in production deployments and with catastrophic thrashing. So things would run fine, and all of a sudden you'd get thrashing and the whole thing would just crash. You could not, the console would become unresponsive. You could not submit a new job, okay? It was that bad. And not only this, but it was actually kind of pretty common in the 60s for this to be a problem. It was such a big problem that IBM didn't want to ship a virtual memory-based system until IBM felt that they had solved this problem. So there's multiple other ones out there already. So in the mid-1960s, IBM launches a big effort to study eviction algorithms for their virtual memory system because they were getting demand from programmers in the field who did not want to program anything other than virtual memory, because why would you, right? If you have virtual memory, just everything is so much easier because you have zero-based and range for your memory allocation. So reluctantly, or by necessity, they started this project, which actually led to a sequence of events that ended up in the work that we did. Okay, so let's see, 1966, as part of this project, Bellotti publishes when trying to study LRU, publishes a paper which has an extremely high number of citations because pretty much all of us, at some point in time are dealing with memory management or cache replacement policies, and we have to compare against the dreaded MIN, right? So this offline optimal algorithm goes back to 1966. So now you can see 62 to 66, already we've gone through this cycle of understanding, hey, you've got to do better memory management. You have to study this fundamentally and formally. And this seminal paper is published. And interesting, again, this could be from FAST this year. One hopes to improve replacement decisions by anticipating future references on the basis of previous references, right? So we are definitely building on the shoulders of giants here. Something interesting. So on the left-hand side is a plot from Belotti's paper, which has cache size on the x-axis, and then frequency of access on the y-axis, and it's really interesting. Like similar plots are published in papers today, and so this is the first one that I found that actually plotted a missed ratio curve. It may have existed before, I'm just not aware of it. And the way they constructed this was by running multiple experiments and drawing lines between them. And this is how you could tell what the shape of the workload was in its cache efficiency. Okay, very, very important thing. And so this is published in 1966. Between 1966 and 1970, people already got tired of running lots and lots and lots of experiments to try to draw these curves. So in 1970, Dick Mattson at IBM again publishes his seminal work, which is a one-pass algorithm to draw the entire curve for algorithms of a certain specific type, which Carl alluded to, which are called stack distance algorithms. So this is revolutionary because now you can just run one single pass and get the full curve as long as the algorithm is stack distance, which many at the time were. Only recently have other ones become more fashionable. And so now we are at 1971. This paper is published, but adoption is very low in industrial settings because for long traces, it's very hard to run because it's an expensive algorithm. So over the decades, improvements are done on the data structures, but not the algorithm, the complexity of this algorithm. And that's where Carl, Alex, Nohhyun, and I, in 2012, I think, we are sitting there trying to figure this out, starting from that and realizing that, hey, this algorithm is like what you want to do. It's just too expensive, and that leads to the approximation algorithms that Carl referred to earlier. So a couple of funny stories. So when we were writing this paper, you're supposed to cite sort of the earliest instance of something that you want to refer to. So in this case, this was the clock algorithm. So a couple of us were discussing, saying, hey, when's the last time you read the original clock paper? And I hadn't read it. So I said, I haven't read it. I'd like to go find it. Well, we searched on Google, and we searched on every search engine you could imagine to try to find a PDF of this paper. We couldn't find it. And we're like, how is this possible? How is this not on the internet in, 2014? Maybe it's 2015. And so we reached out to some friends to go look on the shelves of the MIT libraries to see if you could find Corby's, Fernando Corbato, Turing laureate, and responsible for leading the Multics project, from which comes Unix, from which comes everything that we use every single day, including operating system on this laptop. So Saman, I guess, he couldn't find the papers at the MIT libraries, and then a panic ensues. How is this paper that has been cited thousands upon thousands of times not on the internet, not at the library? So what have we been citing? Like, has anybody read this paper? Where is it? So thankfully, Saman, a professor at MIT, was able to get a hold of Corby, who at that time already was, retired for a long time and very old, in his 80s, on vacation. And Corby responds while on vacation and says, hey, I'm surprised that there's no copy of this. I think I have a copy of this in a box in my attic. And so, again, panic continues. We hope he has a copy of this paper because nobody else has a copy of this paper. So anyway, he comes back from vacation, finds the paper. We got a PDF, and now finally it is on multicians.org. You can actually just search for it. You'll find it. So just fun stories. We will all go through interesting, adventures and fun incidents that happen. So we wanted to just share a couple of them. Thank you for your attention, and thank you to the committee for the honor. Please.
Hello. Hi. I would like to thank the committee and the co-authors for, it was a fun project. I still remember it was like 10 years ago, but I still remember it pretty well. I first heard about the idea while I was interviewing with Cloud Physics. I hadn't actually joined yet. And in a cab ride, I wasn't sure, I'm not sure if it's cab, but in a car ride, Kyle mentioned this idea. And I thought, that's not going to work because I/O processes aren't stationary. So if you sample, you're not going to get the average behavior. I actually said it. And I had met Kyle for the first time, I think, on that day. And then Kyle said, oh, yeah, but let me try it anyway. I went back to school. I think a few weeks later, Kyle sent me this data. Hey, here's like preliminary data with these traces. And I spent like whole day trying to show why it doesn't work. And I think I was fairly skeptical until a few months in. And then once I was bought in, I was confused and also try to figure out why it actually works. And that was kind of a fun journey for me. So yeah, thank you.
Thank you. I'd also like to thank everyone. It was a really wonderful experience. I'd like to pick up on one thing that Carl had said, which was the amazing accuracy of the algorithm. And in particular, one thing we came up with was this notion of the adjusted shards algorithm. And the basic observation was that what you want from a sample and a simulation is something that has fidelity to the full-blown set of events, right, as if you hadn't sampled at all. And the key observation here was that how could we take sort of something that's easy to measure about the overall run, for example, of a trace, and compare that to how our particular sample had done, and then adjust the sample to be even closer to the original. That the basic observation in the case of MRCs was that what you're measuring in MRCs are basically events, right? They're axes. And even though we print them as ratios, really what you have are counts at each distance, right? And the observation is that the counts, the further you get to the left, the longer the distance, right? In some sense, the fewer of those there can be, because because they're at a greater distance, they depend on a lot of other events of having happened in between. It has an interesting property, actually, in the case of sampling, because the larger the distance, the more events had to happen to lead to that distance. So the more likely your sampling will have picked up that signal, and you'll get something out there. The other thing, though, is the less, if you oversample sort of the things that are far or the things that have the greatest distance, it's hard to do because there aren't that many events of that kind, because they depend on so many other things to have occurred in between, right? So the observation was that if there is an error, the error is going to be actually right down in the small distances. It's not all going to be at the very smallest distance, but it's mostly going to be there, right? Those are the things where you're either going to under or overcount, and when you do, you'll get a rather dramatic impact. So what we did with adjusted shards was essentially compute the total number of events that occurred for the full run, right? Compared that to the number of events we actually got from our sample. And what you'd expect is that, if the sample size was a certain percent of the whole thing, you should see the number of events you measure is similarly, right, related that way. And if it isn't, then that actually is a very good estimate of just how far off you are in terms of your error. And so the adjusted shards algorithm basically took that delta and used it to adjust the shortest distance, because that was where most of the error was. And that actually had a profound impact in terms of improving the accuracy. Well, what I like about that story, though, is what it's trying to do is make a relationship between what the sample shows you versus what you know is true about the overall thing that you can measure easily. And then using that combined with identifying some bias in how errors are distributed to then make your simulation actually that much better. And I honestly think that's a more general technique. I've been thinking about how that could be used elsewhere. But anyway, just wanted to share that as well.
Thank you. So I thought I would give everybody a quick update on the research agenda. So I remember sitting down with my co-authors. We were discussing, we were really excited by this paper. I mean, just like the excitement was just absolutely immense because you felt like you were really onto something interesting. And we wondered, okay, will other researchers actually follow up on this work? It's actually kind of an interesting question we had. Like, will other people try to improve this or apply this in ways we haven't thought about? And I think I'm just so happy to constantly back and forth between us, and long after the paper was published, sending each other papers that develop on top of this work and improve it or fix some specific corner case. So that's an interesting thing. So we've also, many of us have published additional works in this area, as Carl has mentioned. We've also now have a proof that the sampling algorithm works and it abounds in its accuracy, which is really exciting. And then there's the intellectual property, the ideas, and the patents that were formed as part of this now were spun out into a new company. It's called Magnition. It's in business. It helps companies that are designing storage devices or cloud block storage or content distribution networks to use these techniques to optimize their memory hierarchies, basically. And I think final thing, I'm pretty sure we can speak for everybody, all of us here, that this is not done. Actually, if you come talk to us, we'll tell you about certain other interesting areas that are unexplored. So if you're students that are interested in high impact work, there's tremendous opportunity in the world of predictive performance modeling of caches and memory hierarchies, and actual real world opportunity for impact in reducing the total DRAM burn in the world, the gigawatts that are wasted in just idle memory. And it's just really, really high impactful work awaits. Thank you.
Thank you.